Yeah, let me apologize to begin with for I'm not as good a speaker as David Rolich is, and also the second apology is this is a last-minute stand-in, so I didn't prepare an abstract or anything as nice as some of the other speakers did. Instead of an abstract, I will scribble very briefly a very short abstract on the blackboard now, which will serve for today and for tomorrow. So what my plan is to cover roughly half of the 6 items I'm going to write down today and the other 3 tomorrow. So this will all be about modular curves. I was supposed to use this thick thing, which is impossible unless you break it, of course. And wow! Modular curves. And the aspects of modular curves we will address is, first of all, we'll look at these things analytically a little bit. And then we will look at them to a slightly more extent algebraically. After we've seen the modular curves, we will look at correspondences on the modular curves. And then we reduce some Hecke correspondences modulo primes, and we run into what's called Eichler-Shimura. Maybe Eichler-Shimura, if I'm modest, congruence relations. Four. Maybe we put one in between, which is called Shimura-Taniyama way. Because it fits in. And then finally we will look at the representations attached to modular forms and speak quite briefly, I hope, because I'm certainly not an expert on this at all, of how these representations look like when you restrict them to a decomposition group. I think these things were called GLB this morning. And that's an outline of everything that will happen. So we start with modular curves. So I'm assuming that you're not an expert at all on modular curves. So this means some of the people in the audience won't hear anything new. The lecture is simply not addressed to them. I'm sorry. What modular curves are is they are, we can say, catalogs of elliptic curves. Plus, elliptic curves which are given some additional structure. For instance, what one can do is put no additional structure on elliptic curves. So these are examples. You just look at elliptic curves up to isomorphism. And if we have, as we have seen in, for instance, Joe's talk, these things are simply described by their J invariant. And if you want, you can see the J invariance as an affine line. So, and this will lead in the end to a modular curve which you may call x1 or x01 or x11 or whatever you want. And then you can look at another example. You look at pairs, say an E and a C in which you demand that C is a cyclic subgroup. Let's call C Cn. So Cn is a cyclic subgroup of order n, which is inside the n torsion of E, maybe over an algebraic closure, if I want to work over some field. And I look at these things up to isomorphism. That means I look at isomorphisms of E to another E, which send the one cyclic subgroup of order n to the other subgroup of order n. So I cannot look at all the isomorphisms anymore. I have this extra constraint on the isomorphism. The cyclic subgroup has to be respected. Well, as this leads in the end to a modular curve called x1, this leads in the end to the modular curve that we've seen before, x0 of 1. X0 of n, where n is this n. And in this fashion, there are many more. You have also pairs like here of E, and now not a cyclic subgroup, but a point of order P point of order n, exact order n. And in the same way, this leads to a modular curve which is called x1 of n. There's a somewhat harder example in which you take pairs E and let's call them phi, in which this phi is an isomorphism from the n torsion points to z mod n squared, which we assume to be symplectic. That means on this En we have the Y pairing as we have seen. So here we have the En pairing. Now on z mod n squared we can also put a symplectic pairing. For instance, we take the pair uv and z mod n squared and xy, and we can look at the pairing, say determinant, so u times y minus v times x. And then symplectic simply means that phi respects this pairing. So what is it? If I take 2 points here and take their phi images, they pair to the same thing as they did before. Well, this leads in the end to x of n. And then there are some other less general modular curves that you don't see that often, but that play a role in some technical points in Weil's paper. For instance, in section 2, I mean, all the things between proposition 2.3 and 2.8 or so, you find curves which are called, for instance, there's one that corresponds to triples. These are triples of the kind an elliptic curve, a point P, which, what does P have? Order n on E, plus a cyclic subgroup of order Q. And then I probably demand that the GCD of Q and n is 1. Such triples up to isomorphism. Well, this what do I do now? This leads to another modular curve, which is called the x1 of n and q. And then there is a gadget called the x1 of n times q and q squared, which also plays a role. And that corresponds to slightly more subtle triples. It's an E, it's a P, and it's a subgroup of order Q squared. But now this P has order n, so n times Q. And there is a relation between the two, namely if I multiply the subgroup by Q, then I get the same subgroup that I get when I multiply this point by n and take the subgroup it generates. So this is a modular curve which is in Weil's paper is called x1 of nq and q squared. So this is just examples without, I mean, I'm defining sets at the moment, as you see. So now something is going up. And something should go down, I hope. Which one was going down? This? This? Okay, so now we try to build these sets into sets having a little more structure. And that brings us to point number one. Namely, we will do this now analytically. I guess this is rather familiar to most of you. What does analytically mean? Well, we simply do it over C. So what do we know over C? We've seen in Joe Silverman's lecture that over C, an elliptic curve corresponds to a complex torus, a complex one-dimensional Lie group, to C modulo a lattice. And when are two of these C modulo a lattice isomorphic? Precisely when the one lattice is a constant times the other. When the two lattices are homothetic. So this makes it rather easy to, in terms of the lattices, to describe elliptic curves over C. So now, I mean, what you do is, this is of course a very convenient way of describing the isomorphism, but we somehow like to have a more convenient way of describing the lattices. So what one does is one first uses a homothety to get the lattice into the form, so z plus z times tau, where this tau is in the upper half plane as before. And then what does it mean that two such things lead to the same elliptic curve? Well, then a homo between two of these simply means that we have to multiply this by some complex number in order to get this, which means that the two basis vectors of this as a modulo over z have to be mapped to two things here. It's just changing bases in Z2. Well, that's done by an element of GL2, as we know. So, but also we have this restriction that the tau and the tau prime are supposed to be in the upper half plane. So this will happen precisely when the tau prime is of the form A tau plus B divided by C tau plus D, in which you demand that the matrix ABCD is in SL2Z as positive discriminant. So this, as we saw before, defines an action of the modular group SL2Z on the upper half space. So what we see from this is that isomorphic classes of E's over Q over C are in one-to-one correspondence with, well, this action is probably on the left, so I have to put this SL2 here to this. And now we can take any of the problems we have over there and try to describe them in exactly the same way. Well, since you must have seen this before, let's look at it, the x0n case. Recall x0n had to do with pairs, an elliptic curve and a cyclic subgroup of order n. So what does that mean in our case? It means we have C modulo Z plus Z times tau plus a cyclic subgroup of order n. Yeah, this means we have something here which we divide by n. Now I can use a homothety to begin with and change tau a little bit so that the subgroup is the subgroup 1 over n. Or if you want, I can choose my basis for the lattice in such a way that the basis is an omega 1 and an omega 2, and that my subgroup is generated by omega 1 over n modulo the lattice. And then I divide by plus or minus omega 1 in order to stay in the upper half plane, get my tau, and have this subgroup. So these are the things that I want to classify. So I have to describe them up to isomorphism. So what is a isomorphism? It's a homothety between two of these lattices, which is something like this. Well, this here, if you look at it carefully, means that the basis vector 1 here is multiplied by the C tau plus D. So isomorphism given by, let me say, A, B, C, D. What does it do? It sends the cyclic subgroup to the cyclic subgroup on the other curve, the one with the tau prime, which I didn't write down, C tau plus D over n. And what do we want? We want that this is exactly the same subgroup as this one. So we demand, that was what I was describing at the very beginning, we don't just want isomorphisms, we want isomorphisms that preserve the additional structure, so that send this subgroup, this distinguished subgroup on the one, to the distinguished subgroup on the other, and I have said at the beginning that I want my distinguished subgroups to be 1 over n. So what we demand is that this C tau plus D over n equals the 1 over n modulo the lattice. And if you look at this simply means, well, they have to be in the same direction and they have to generate. This simply means that the n has to be a divisor of C. If I would take the second moduli problem, the x1 problem, so a point, then I don't just want that this subgroup is invariant, but I want that this very point here is invariant. So then it's not enough that the C is a multiple of n, but also I want to stick to my fixed point of order n, 1 over n, which means that the D has to be 1 modulo n. So what we see here is the following, that isomorphism classes of pairs E and a cyclic subgroup of order n over C are in one-to-one correspondence to the upper half space where I mod out, now not the full group SL2Z because I have this extra constraint, but the subgroup of SL2Z, it happens to be a subgroup of all matrices where the C is a multiple of n. And this subgroup is called gamma 0 of n. And similarly, we have gamma 1 of n for the other, and you can easily write down all the relevant subgroups of SL2Z that correspond to any of the moduli problems I wrote here. So still, what am I doing here? I still have these things now of the complex numbers as sets, only the sets are a little bit more explicit. I didn't put any structure on the sets. So I don't want to put too much stress on the analytic theory, but let me just, it is possible, and in fact rather easy, and it's classical. to put an analytic structure on all these upper half spaces where you mod out such a group which I call gamma. It's not very hard. This action is basically discrete. There's a little problem because, well, since I write SL2, there's always a stabilizer, namely the -1 matrix, but I might as well say that the PSL, and so the group modded out by the normal subgroup plus or minus 1 is acting. But then still some of the points have stabilizers. So it means if I take little neighborhoods here, then a little neighborhood of a point which is stable for still some part of this group, I have to be slightly careful in defining the analytic structure. But the stabilizers are finite and it doesn't really cause a problem. There are only 2 such points where you have to do something. So then what you get is the neighborhoods here look like little pieces of complex planes. So what you get is a Riemann surface. In fact, you get an open Riemann surface. There are many easy-to-read books that describe this. For instance, for the case of SL2Z, a course in arithmetic by Serre already does this. Chapter 10, I think. Somewhere way in. So you get an open Riemann surface, and you can compactify it in an. So it can be compactified. Actually, also in a very easy way, namely, what you add to this upper half space is the rational points of P1, and the action you already have easily extends also to this union. And then as a set, again, you have this thing, and, well, it turns out you get a compact Riemann surface. So what you have now is Riemann surfaces in which a large open part describes nicely the points over C, which correspond somehow via this tau to elliptic curves with the additional structure you had. So this is the analytic approach, which is dealt with in many books. So what this gives, so this approach, let's step back and see what it gives. One thing, as you already see from the vague and brief description here, is it's very explicit, which is nice. It's somehow elementary and easy, which is also nice. Another thing is it's good for certain computations. For instance, using this description, it's easy to compute you get genera, so the genus of such a Riemann surface. Also, what you get nicely is a theory of cusp forms. Namely, I won't even write it down, but what this corresponds to is this is a Riemann surface. So you can look at holomorphic differentials, holomorphic 1 forms on it. And then you can pull back such a holomorphic 1 form to the upper half space. And there, look, in any of the local coordinates you have to be careful what these local coordinates are at the points which has stabilizers and also at the cusps, these extra points at the compactification that you made. But you get these things. And what you end up with are functions, holomorphic functions on the upper half space, which have a certain, transformation behavior in terms of this group gamma. And it's all very nice and explicit and easy to give, and you get the dimension of these spaces of cusp forms because they correspond easily to these differentials. So you have all this basically for free once you've set up this theory for this. There are also drawbacks to this. How do I proceed now? This is tricky. One has to go down, the other one up. There is a third, but someone said I shouldn't use 3. As you see, juggling with 2 is already almost too hard for me. So before I keep erasing, what are the drawbacks of this setup? Well, there are 2. One is, as you see, you have absolutely no arithmetic. Well, it's not completely fair to say this, because even in this way, you already have some arithmetic. I mean, if I want, I can... so let's say, well, we can write down our first version of Taniyama Wei already now. Let's do this. We have... So Shimura Taniyama Wei. I forgot one of the 3, I guess. Huh? So first version, which I do just from this description. Actually, I could give a first and a second. So let's start with an elliptic curve over Q. Then to this elliptic curve is attached an L series, which will be in Joe's lecture tomorrow. I don't think he wasn't. Well, he had the Euler factors on the blackboard, essentially. So, but there is a function here, and this L series looks like a function of the form a Dirichlet sum sequence, sum an over n to the s, in which these an are certain integers. So now what we will do is we completely ignore this n to the s and do Mellin transforms or whatever sophisticated people say here. We write down the sum an and then q to the n and multiply this by dq over q, in which this q is e to the power 2 pi I times, let's go, I have to call it tau here, I think. Also, this is something where people are mixed up. I mean, in all the lectures so far, it's tau. In Weil's manuscript, it's z. But in Joe's lecture this morning, there's another z. So what this is a local coordinate at infinity, at I infinity in the upper half, well, extended upper half plane. So what is this? This is a differential on the upper half plane. Well, actually, what Shimura Taniyama Wei says in the conjecture is that this is actually a holomorphic differential on this x0n. Should I call it that? Well, it's not quite consistent with what I did so far. Let's say on the group gamma 0n acting on this extended upper half space. It's better. So this is the first version of, so I was talking about drawbacks, but here is something that's not quite a drawback. I at least have a formulation, only the formulation doesn't help much in proving it. So no arithmetic is one drawback. Here is the other drawback. At some point, at the very end, in fact, we have added some points. We have added these cusps. So the additional points which are called cusps for classical reasons. They are no cusps, but they are called cusps, Spitzen. They have no interpretation. In terms of classifying analytic curves here. So, I mean, it's nice for some, well, you get a good theory and really something worthwhile to give courses on, but it has drawbacks. So we go to the second arithmetic, so the arithmetic approach. Actually, there are two arithmetic approaches. There is the modern one, and the modern one is really nice because it takes care of everything. It does give you arithmetic, that's why I call it an arithmetic approach here, and also it takes into account that you'd like to have some interpretation in terms of classifying some generalized elliptic curves and maybe generalized subgroups or whatever kind of additional structure you put on them. So there are two kinds. The one is the moduli one, which is really wonderful, beautiful, gives you everything you want. What it leads to not just modular curves, so over fields, but let's say way more. You get them essentially over Z. Or maybe I have to invert some primes, or have to extend Z a little bit, I mean add nth root of unity, but you get them, well, what you get is some beautiful, almost continuous way to see, I mean, I'm talking about the language of schemes, of course, in which you get fiber by fiber all the modular curves that you ever wanted. And not just that, any additional point you have, I mean, on these beautiful spaces has an interpretation. So this needs the language of representable functors. You get coarse moduli schemes in general. And, well, it's very nice, it gives you everything, but it's not so easy to describe in a, say, half-hour lecture by now. So the other one is the more classical approach. And that is, you describe modular curves arithmetically by giving their function fields. And maybe Shimura was the one who also Igusa has, for other cases, looked at this quite a bit. It's not as good as the second approach, which I don't take, but it serves our purposes quite nicely. So I will stick to that and try to do it in as much detail as I can possibly do. So what happens here? I cannot describe all the modular curves in the same detail that I had on the blackboard so far. So we focus on this x0 of n, which is a curve which I didn't define yet. I only defined what its points should be. The points should correspond to isomorphism classes of pairs, elliptic curves, and the cyclic subgroup of order n. So what we do is, first of all, we choose a transcendental T over C. Yeah, so that, well, the field C of T is the purely transcendental extension of transcendence degree 1. And then what we do is, if I take this T and adjoin it to Q, what you do is you pick, just at random, an elliptic curve with J invariant T. I mean, these things exist. If I get any number, and in this case I take the number T from this field, you can well, I wrote down some examples. So if I didn't make, we have these formulas of this morning for the discriminant, so you can easily check, and for the J invariant, so you can easily check whether the J invariant of this thing, so 27 times t, you divide by t over minus 1728, multiply this by x, and then the same number what you do is you write down 4x cubed minus a, and solve for a in order to have J invariant t. And then here you have a solution. Or there are more examples. This one is somewhat nicer in the sense that it also works in different characteristics, like characteristic 2. This one, x cubed minus 36 divided by the same t minus 1728 times x minus 1 over t minus 1728. So here are two examples of elliptic curves having J invariant t, which are defined over Q of t. So recall what I was doing. I'm trying to describe modular curves by giving you the function field of the modular curve. So here you have this, so I'm trying to repeat the trick that I did a moment ago. One has to go up. No. So now I'm trying to write down this function field, and it's something very simple. It's exactly what you will think if you think a while what it should be. Namely, what I do next is I have picked my elliptic curve, so now I pick Cn on E, which is of course not defined, or of course, well, it turns out not to be defined over Q of t, but over an extension. So you pick this Cn. There are several choices. There are n plus 1 choices of this. That's true for n is prime. And now comes the definition. My function field will be, I take the fixed field in an algebraic closure of Q of t of all the sigmas in the absolute Galois group which have the property that this sigma sends the cyclic subgroup to itself. I mean, it acts on the cyclic subgroup because, I mean, if I give coordinates like this, it acts on the coordinates and sends points of order n to points of order n. It's just the kind of representation that we've seen before. So I take these sigmas, and I take this fixed field of all of them, and that will be my function field. Is this really a function field? So first of all, this gives a finite extension of Q of t, which is, I guess, clear because, for instance, it is contained in, if I adjoin to Q of t all the coordinates of all the points of order n, then I get a finite extension because there are only finitely many such points, and they are all algebraic over Q of t. So I really get a field of transcendence degree 1, hence I get this is a function field of a curve. So we have a function field so the next thing is what I would like to have is that I really get the function field of a curve over Q. This means when making this extension, I have not secretly added the square root of 2 or some nth root of unity or any element that is algebraic over Q. So this is the claim and the proposition that takes a while to prove. Claim my function field here, if I intersect it with an algebraic closure of Q, then all I get is Q itself. And to prove this, we will need a lemma. Maybe before phrasing the lemma, let's look at this field again, or more generally, if I adjoin all the points of order n on an elliptic curve to the field where the elliptic curve is defined on, then I certainly have added the nth roots of unity as well. And actually, as Joe told us, adjoining these nth roots of unity simply means that that I restrict myself. Here, the Galois group here, I can see as the, inside the automorphisms of this, inside the GL2, or the GL of this space. So what I'm saying is that adjoining this nth root of unity means that inside this GL, you look at the SL part. So let me, after the lemma, already make the remark here that if I have an E over K, and I have an extension of the following type. Here I have K, there I have K to which I adjoin the nth roots of unity, and here I have K to which I adjoin all the points of order n on an elliptic curve. So this here is a Galois extension. Maybe I should assume that the characteristic of K has nothing to do with n. So, but this is Galois with the group inside GL2. And what this corresponds to is simply the Galois extension, which is the determinant of this G. And what this corresponds to is the subgroup, which is the G intersected with SL2. This is quite general. So this means, for instance, if I, instead of looking at this over Q, I prefer to look at this over the complex numbers, for instance, or over Q bar, then I already have this part in my field, and then G intersected with SL2 is all of it. So what we always have is that if the nth roots of unities are in my field, then I can regard my Galois group as sitting inside SL2. Now, the lemma is that if the J invariant of a curve E is T, and I look at the extension, did I write this down somewhere? I hope I did. I look at the extension well, I'll describe the Galois group of this, which I just try to explain is a subgroup of SL2, but actually it's all of SL2. This extension is as large as it possibly can be. And well, there are two ways of proving this. I mean, what it means is that what you have to do is find enough functions in here. And one way of doing this is looking at your curve as some sort of general curve in the, well, depending on the tau in the upper half space, and then trying to see this as an extension of function fields of modular curves in the complex setting, so as fields of meromorphic functions. So you build some meromorphic functions, and in that way give this extension. I got for these notes 4 or 5 days ago some pages of preparations of David Rohlich, and one of the things that he was doing very extensively was actually building these modular functions, giving such an extension for an extension of modular function fields. You can also make it plausible by looking at the interpretation here. Namely, what you get here is, well, this sort of extension very much looks like an extension of modular curves. And this should correspond to an x1 over the complex numbers. And here it seems you have some sort of full level n structure. And then it's not so strange to see that looking at this quotient map here, it's the SL2 of Z mod NZ, exactly what lies in between. And maybe I haven't checked this at all, but it occurred to me when I walked to this lecture that there might be a full proof of this in Serre's abelian analytic representations and elliptic curve, because this curve T. Oh no way. No, this doesn't work, because at infinity this has best reduction. But still, maybe, well, I'm not convinced. By looking at infinity, you may have a chance of, well, this elliptic curve will have potentially multiplicative reduction at infinity, and that's the reason I think that you have some chance of looking at a local extension there and proving it. But we will accept this now. I hope by these remarks I have at least made it somewhat more plausible. And then see how we can... So, what is a corollary to this? Let's look at our extension again. Now we have C of t. I will assume again that this E is over Q of t. To C of t, I adjoin the points of order n on the elliptic curve. You know what kind of Galois group extension this is. And here I have the subgroup. For instance, I take the nth roots of unity and I take t. And I can try to adjoin, well, the nth roots of unity and t and all of this. But if I have all of this, here again. So here I start with a smaller field. So what I a priori know is this extension is at least as large as this extension. But on the other hand, as this argument shows, it is contained in SL2. So what you get is that this extension here also has SL2 as Galois group. So with here, I mean here. So this is the first elementary corollary. Now I keep giving some elementary corollaries of this kind, and then we have our curve over Q. The second one, which is also an interesting one, is if I do the same thing with all of this E of n, and intersect this with Q bar, then what I get is I get the nth roots of unities. For sure I get those from the formalism of the Y pairing, but no more. And the reason, suppose this equals L, then certainly L contains this Q zeta n. And now I do the same thing here. Well, I put in this L of t here, the extension here, and repeat the argument I gave here. It has the same Galois group. So I get the Galois group of L of t and En over L of t is this SL2 over Z mod n. So what we get is, I do Q zeta n and adjoin t. This is inside L adjoin t. This is inside, well, this thing here, QTEN. This is the same Galois extension as this. So these two fields coincide. So these algebraic parts coincide. So this is also something to reflect upon. This means if we were trying to make a modular function field with full level n structure somehow, then we get stuck in this approach a little bit, in the sense that we only get modular curves over q zeta n. Now this is slightly confusing, because there is certainly a modular curve x of n, which is a curve over q. And the difference is in the problem that as a moduli space, you should look at it over q zeta n. Actually, this difference is even used, probably in Carl's lecture or so. Okay, I'll stick to the same blackboard now to avoid difficulty. Does this mean we have finished this proof? Basically, because let's look at the next part of it. Now, what kind of extension do we have? We have q of t. We have q, where I join zeta n. And then we have q t e n. And what do we know now? We have seen that this here has as Galois group SL2 of z mod n. And this, well, this has the full determinant part. When it's adjoining nth roots of unities. So what we derive from this is inside GL2, and it's as big as GL2. So this has Galois group GL2 of z mod n, this whole extension. And my function field, which I was trying to make, is between this one and this one. So what we are doing is we are modding out, or we are taking invariance under some subgroup of the full GL2 of z mod n. So what kind of subgroup? Well, we have chosen our cyclic group of order n, C. And what this means is exactly what I'm trying to mod out here is for some choice of basis in which a generator of this subgroup is one of the basis factors, an upper triangular group. So what I see from this is my function field corresponds to fixed field of an upper triangular group up to conjugation in GL2. Now, if you look at the determinant from such an upper triangular group, it's surjective. So this means this piece is as big as it used to be. Even if I look at just this algebraic piece, if I just look at this, this function field here. So from this, I get that my function field intersected with q bar indeed equals q, what I wanted to have. And I get two more things. And one other thing we see here is that my construction of this function field doesn't really depend on the choice of the subgroup. Because, I mean, if I had taken another subgroup, then I had just conjugated this group here inside this GL2. So up to a Galois isomorphism which fixes Qt, which means up to Qt isomorphism, this extension is just one fixed extension. So function field doesn't depend on the Cn chosen. And the next step, it also doesn't depend on the E chosen. Why is this? Well, the reason why it doesn't depend on E is that this E has J invariant T. So if I picked another E having J invariant T, and the two E's, well, they are twists. In fact, they are quadratic twists. So in terms of an equation y squared equals something, it means I put some polynomial or rational function in T in front of the y squared. So what does that change in such groups? It certainly doesn't change any of the x coordinates. It does change y coordinates. here and there, but not the x coordinates. Now, what is the beautiful thing? In such an upper triangular group, you have the matrix -1. -1, -1, 0, 0. So anyway, you are in the fixed field of that. So anyway, you might as well have chosen your function field as just given by adjoining x coordinates. So that's, I mean, I didn't write it down now, but that argument is as easy as all the other arguments. It's just applying elliptic curve theory. So this curve here is much more canonical than you would have expected at first glance. Okay, that gave me my second part of the talk. Also brings me very close to the end of my notes, which means I have to do some preparation in order to get notes for tomorrow. There's one more thing I want to say about this curve, and that is I want to hook it up very slightly to this modular interpretation again. And for this, it's convenient that I kept my equations there. If you look at those equations, both of them work very nicely when I plug in for t a number. I mean, any number in Q bar, except if I plug in t equals 0 or t equals infinity or t equals 1728, then things go wrong. But all the others are okay. And there's no way I can avoid this, because if I have any curve with J invariant t, the discriminant will change up to how things change under twisting to the discriminant of this one. And if you look at the multiplicities of the factors t and t minus 1728 and infinity in this discriminant, you see that you can't get rid of them. Because under twisting, you change discriminant by 6 powers, and there is no way to get rid of a second or a third power or things you have here. It's the same 2 and 3 that appear in these stabilizers in the other story. So the best you can hope using these families is to describe elliptic curves having J invariant different from 0 in 1728. And that's actually what you can. So this is the proposition that is like an exercise. It's very easy to prove. I look at isomorphism classes of pairs E and the Cn over Q bar with the property that the J invariant of the E is not 0 or 1728. J invariant infinity is a bit strange to write down. I don't look at singular curve, is what that means. Well, what this does is it is in one-to-one correspondence. Well, the infinite sets quite often are in one-to-one correspondence, but it's in one-to-one correspondence with something I will call here x0 prime of n. x0, that's the curve that corresponds, that's the curve over Q that corresponds via our construction to this function field, a smooth curve. And what does this prime mean? This prime means I leave out the ones that correspond to J invariant 0 or 1728. And if you think of it, it's quite easy to describe what this map is. Because what are points here? A point here you can see as, well, I'm looking over Q bar. So let me look at our function field times Q bar or tensor Q bar. It's linear disjoint, so I can do such things. My function fields, if I take valuations on this, such discrete valuations are exactly what points on a smooth curve correspond to. I mean, this is basic curve theory. So now what this means is, for instance, I could take, well, in Q bar I take the square root of 2, and I take the valuation t minus square root of 2, which is a valuation over Q, but if I extend it over Q bar, then it's still, oh, no, sorry, there's a little problem because I also extend the t. But I make an extension of that valuation to here, which means that reducing modulo such a v, I'm plugging in square root of 2 for my t, and since I've done it on a higher level, I can also reduce my subgroup. So what you do here is, the map is that any such v, such evaluation inside here, is simply mapped to, I pick my e, it doesn't matter which e I take, and I reduce it modulo v, just in the same way as you reduce curves mod t or whatever. And I take my subgroup and reduce it mod v. You have to look at twisting a little bit to see that this works. But this is rather easy, and it gives you the modular interpretation again. So this is some arithmetic description of what these modular curves are. I will stop here. And so do the